Hello everyone, welcome back to Techno Fame. I'm Shreyash, and in today's session, we'll dive deep into three-phase systems and transformers. We'll cover three important aspects: phasors, star and delta connections, and finally, how to handle unbalanced loads. By the end, you'll not only understand the concepts, but also see how they're applied in real-world electrical systems. So let's begin. First, what is a three-phase system? It is an arrangement where we have three alternating voltages of the same magnitude and frequency, but displaced in time by 120 degrees. Let's visualize this with a phasor diagram. Notice how the three voltages are equally spaced. This balanced nature is what makes three-phase systems so popular. Compared to single-phase, we get smoother power, higher efficiency, and smaller conductor sizes for the same power delivery. Important terms: line voltage VL, measured between two lines; phase voltage VPH, measured between line and neutral. In star connection, VL equals square root of 3 times VPH. In delta, VL equals VPH. Similarly, line current and phase current relations change. We'll see that in detail shortly. So remember, three phasors, 120 degrees apart, is the foundation of everything that follows. Now let's move to star and delta connections. These are the two most common ways to connect three-phase systems. Star-Y connection. Here, one end of each phase winding is joined to form a neutral point. This allows us to connect both line and neutral wires, which is useful for supplying single-phase loads as well. The relationship is VPH equals VL divided by square root of 3. Delta connection. In delta, the ends of the windings are connected in a loop, forming a closed triangle. There is no neutral, and line voltage is equal to phase voltage. Current relationship is IL equals square root of 3 times IF. Where do we use them? Star is common at the consumer end because we can provide both single-phase and three-phase loads. Delta is preferred in transmission and for induction motors, where high power is required. Quick example: suppose we have a 400 V line in star connection. Then the phase voltage is 400 divided by square root of 3, which is about 231 V. This is the standard household phase voltage in many countries. Now let's talk about what happens when the system is not perfectly balanced. In theory, three-phase systems assume equal loads on each phase. But in practice, loads may differ. For example, if one phase is supplying more single-phase equipment than others. This is called an unbalanced load. In a balanced system, the three currents sum to 0 and no current flows in the neutral. But in an unbalanced system, the vector sum of currents is not 0, so the neutral conductor carries current. Methods to handle unbalance. Use of a neutral conductor. In star connection, the neutral provides a return path. Delta connection, circulating currents inside the closed delta help balance the load. Special transformer connections. For example, delta star provides a path for harmonics and helps maintain balance. Let's quickly recap. A three-phase system consists of three voltages 120 degrees apart, represented easily using phasors. Star and delta are the two major connection types, with different voltage and current relationships. When loads are unbalanced, neutral conductors, delta windings, or transformer arrangements are used to maintain stability. That's all for today's session on three-phase systems and transformers. I'm Shreyash, and you were watching Techno Fame. If you found this video helpful, don't forget to like, share, and subscribe. Thank you for learning with me, and I'll see you in the next video.